There. All right. Good morning. It's a full house here, so hopefully it's not too bad. But it's all pretty fun. Okay, so yesterday we finished talking about the Z table. We started using the Z table a little bit. So now I want to just kind of do a quick review, right? And so what we said was, okay, what if we have review? I need a little bit more space here. No such luck. Okay, that's okay. So a little bit of review. We started talking about the normal distribution, of course. And so we said, okay, if I have a normal distribution and I'm given, oops, sorry. It's too early for me. We always meet at 8, I know. X follows a normal distribution with some center mean mu and some standard deviation sigma, then down here in the center is our mu, and then sigma equals the standard deviation, whatever it is, we kind of jot it down on the side. And then how we use this is we say, okay, well, if I have some observation X that I'm interested in finding a probability with, then I can use the mean and the standard deviation to standardize this value. And then I use the standardized value to find the probability. Okay. So given an observation X, right, we can find a probability associated with it. We can find a probability associated with it, or associated with X, right? Either less than or greater than X, by standardizing the value, by standardizing the value, which means calculating a Z score, right? Where Z is X minus mu over sigma. Okay. Then once we have the standardized value, typically we would use software, right? And even software would just calculate the Z score for you. So, but it does it internally, typically. And then, but then what do? We go to the table, right? Once we have a standardized value or a Z score, right, we use the Z table, right? Old school, but that's what we're doing. We use a Z table. We use a Z table to find the probabilities, so the areas under the curve, to find the probability we need, right? Which is really just the area under the curve. Oops. So let me pull up. Let me see here. Move the chat a little bit so I can see it. Okay. I didn't need my face down there. Crazy. Also weird that I didn't notice. But anyways. Okay, so how I like to kind of visualize this is through kind of this chain, right? And so what we have is we have some observation and we turn it into a Z score, right? And how do we do that? We use Z equals X minus mu over sigma. Okay, so that's how we go from an observation to a Z. Okay, so that's true. And then from a Z to a probability, right? Some area under the curve. How do we do that? From the z-score, we use the z-table. Use the z-table. Okay. So now it's not that crazy to think that, and this is kind of the end of the review, I guess. Let's put it here. It's not that crazy to think that if I give you a probability, right? So I give you some area under the curve, then you can turn that into a z-score, right? Just using the z-table, but now you're going to backtrack, right? And we haven't done a lot of practice with the z-table, so I know it's a little bit weird still, but we're going to do more practice, right? And so, but we can take a probability, we can turn it into a z-score by backtracking in the z-table, and then I have a z-score. So now all of a sudden I have a z-score, and I know mu and I know sigma, so then I can solve for x, right? And so we can also move this way. So from a probability, or maybe here, we can also, I think of it as working backwards, only because this is the way that I introduce it first. And so here, we can also work backwards. Which by that, I mean, given a probability, we can work backwards to find an observation. Given a probability, we can find the observation associated with it. Associated with it. Okay. So then I'm going to steal this, and you can just write on it again. Okay. All we're going to do is we're going to say, okay, well, then I'm going in the reverse order here. But from the probability, right, we can use the z-table still to find the z-score, and then we can use that z to solve for x. Okay. So now, how about we do an example? I kind of think of z as like a gateway drug, right? And so I kind of think of it, okay, we have to go through z in order to get anywhere. Right? So in the textbook, I had one picked out. I'll put it in our notes. So what if we have an example like this? So Eric's height is at the 40th percentile. Okay, so let's remember that the 40th percentile means that there's 40% below it and therefore 60% above, right? So let's remind ourselves here, right, about percentiles, because now we're going to be able to talk a lot about percentiles, right? Especially if we think back to our SAT scores from yesterday, right? We can figure out, okay, what score would I need to be in the 90th percentile, right? Which means I have 90% of the scores below me and 10% above me. Or what if I want to be in the 95th percentile, right? That would be great. So the 40th percentile means that there's 40% below and 60% above the observation. Okay. So we need to remind ourselves what a percentile is. Oh, you know what? I've got this page break here. Maybe I'll put it on the same page. I'm just going to scoot this down here. There. that's better. Okay, so now, first thing you're going to do, even though it doesn't really feel like it, oh, I guess we need to know the distribution for the heights. Here. That might help. I'll put it up above here. Based on a sample of 100 men, the heights of male adults in the US is nearly normal. Okay, good. Can't believe I was going to start this example without any information. Nearly normal, so we know the shape. Okay, good. With a mean of 70 inches and a standard deviation of 3.3 inches. Now I'm completely useless with inches, but let's just use them as numbers. Luckily, they're decimals. Inches are insane. Okay, so we've got the nearly normal part, right? That's good. And let's put the mean of 70. So we know the mean is 70 and the standard deviation is 3.3. Right? And I just kind of jot that down. Maybe it's helpful in the beginning if you write mu equals 70, but as you've probably noticed, I kind of drop the mu because it's obvious if it's in the center. Okay. So, all right. Let's see here. Good. And there was something I wanted to say. Oh yeah. How can we write this in shorthand? This says that X follows a normal distribution with a mean of 70 and a standard deviation of 3.3. That's the shorthand for that blurb. Okay. So now I think we're ready to draw this observation here. Okay. So the 40th percentile, let's think about, okay, the normal distribution is symmetric, right? And so that means that at the midway point, I must have 50% below and 50% above, which means that 40% below would be to the left of the mean, right? So less than the mean. So somewhere here, and it doesn't really matter where you draw it. In fact, I'm going to give myself a little bit more space here by scooting that over because I can. Okay, so somewhere below the mean. This is just to help you visualize the problem, right? And so here, now we're told that this area is 0.40. Okay. 0.4000. But let's just keep it like that. Okay. So then what I want, okay, so we're told, we're given the area under the curve, we're given the probability, right? The probability of someone being shorter is 40%, right, or 0.4. And so how tall is Eric? So here, that's the value that I'm looking for. So remember, I like to use little question marks to show myself where I'm heading, right? And then I need to remember that, okay, if I have a probability, I need to trace it back to a z-score, and then I can solve for x. Okay. So let's see here. This is the area to the left. Remember, the Z table only gives me the area to the left, right? And so I need to make sure that I have the area to the left. Whereas if we were saying in the top 40%, right, then you would have 40% here, and then you would have to convert it to 0.6, right? So just make sure that you have the area to the left, which we do. Okay. So then we're going to say, using the Z table, we're going to find the table entry. Remember the table entry, those are the probabilities. We're going to find the table entry closest to 0.4. Okay. Using the Z table, we find the table entry closest to 0.40. Okay. So now I know I'm going to be on the negative Z side because anything below the mean is going to give me a negative Z. But remember, we're hunting for the Z, right? So we don't know what it is yet. So let me grab the tables, put them in here. So I know I'm on the negative Z side, so that's here, right? And now I'm scanning these table entries, and I want you to be really careful, right? Because there are decoys like this, right? This is not 0.40, this is 0.0040. Oh, did I post it on Moodle? That is a great question. I think I did not, but I will right now. You might have to refresh. Wait, I might have to log in. How about that? Okay, now it's available. Sorry about that. You might have to refresh, but it should be there now. Awesome. Okay. So you want to be careful, right, that you don't fall for the wrong number, right? Something that looks the same. I see that all the time. So that's why I mention it. So the 0.4 is actually going to be closer to the bottom here, right? Because as we move closer to a Z of 0, right, then we're going to get closer and closer to 0.5. So if we scan here, and there is order, right, but it's just how numbers work, right? As we're moving closer and closer to 0, the area to the left gets larger, right? So here is a good jumping off point, right? I see, okay, I've got 0.409, 0.4052, 0.4013, and then it jumps down. So I'm choosing between these two, it looks like. Okay. Sometimes you can take the midpoint, right? And what I'm going to do is I'm going to bring this in. First, I'm going to delete this, and then I'm going to bring in this as well as the top section. Just give me a little second here. There, and because otherwise I'd have to bring in the whole page, and that seems like a waste. Oh, okay, it's the wrong one. There's a bunch of puppies downstairs, and they're all making noise. Okay. So here, I'm kind of cut this off here. There. Ding, ding, ding. Okay. So what we want to do is we want to find the one closest to 0.40. Now we see that there's not one that's exactly 0.40, so then we're going to have to do a little bit of legwork, right? And so I would say that this one is 13 away from 0.4, whereas 0.39, I'm gonna have to bring in my calculator here. 0.4 minus 0.3974 is 26 away. Now that terminology doesn't really make sense. It's not mathy, right? But this one's going to be the closer one. pretty sure. 0.39. Yeah. Okay. So this table entry closest to 0.40, right, is 0.4013. Okay. Sometimes what we would do is we would take the Z in the middle, right? But I want you to use the one that's closest. Okay. So now, right, this is where we ended up when we were working kind of forwards, right? We were working towards this probability and then we were done, right? But now, right, we've found the probability closest to 0.4. So now I can map that back. I can map it backwards. Let's see if I can find a better color here. I can map it back to a Z score of negative 0.25. Okay. So here I'm going to write that down. So using the Z table, we find the table entry closest to 0.4 is 0.4013. Okay. And I'm going to follow that up with a table entry, or maybe I'll say the table entry. There's only one. The table entry of 0.4013 corresponds to, right, or you could say maps back to, or something that kind of makes sense to you, but it corresponds to Z equal to, and remember you start with the whole number in the first decimal place here. Don't forget that negative, right? That negative is going to make a huge difference. That tells you that you're below the mean. Right, so negative 0.25. Negative 0.25. Okay. Good. So now, remember that kind of pendulum, I guess, where we're working towards an observation. And so now we've used the Z table, right? So we were given a probability. Oh, sorry, it's catching up here. We're given a probability. We use the Z table. Now we have a Z, right? And so now I need to use that Z to solve for X. Yeah. So now, oh, let it catch up. Now we use this Z score to solve for X. So Z is X minus mu over sigma. So if I have Z and I know mu and I know sigma, then I can replace those. Negative 0.25 is going to be X, which I'm solving for, minus mu, which was 70, divided by sigma, which was 3.3. Now be careful, right? Because you're going to multiply this 3.3 over to the left-hand side, and then you're going to add 70, right? Just order of operations. So now we have negative 0.2 times 3.3 is X minus 70, which, let's see here, negative 0.25 times 3.3 is negative 0.825, which is X minus 70. So then I have to add 70. So then X is going to be 69.175. I always do this kind of revolving door, right? The equal sign, you can kind of switch it. So whatever I'm solving for, I always put on the left, right? But this is negative 0.825 plus 70. Nice. What does that mean? That means that Eric must be 69.175 inches tall. Therefore, Eric is 69.175 inches tall, right, at the 40th percentile. Nice. So now, right, we've worked backwards, so we can kind of flow through this pendulum, right, remembering that it's a two-step process. Right? In general, if you have this z-score and you want to solve for x, right, we can just solve for x once and for all, and then you can just use that formula. So in general, when solving for x, we can use z equals x minus mu over sigma, which becomes z times sigma is x minus mu. So then x must be, usually I write the mu first, but z sigma plus mu, or x is mu plus z sigma. Notice how important it is that z is either positive or negative, right? So you don't want to drop that if it's negative, right? Important to keep the sign on z, right? Otherwise, your observations are always going to be above the mean if you're always adding them, but that's not always the case, right? So I'll give you this on a formula sheet, right? So you'll have that. So don't worry. Don't worry. Okay. Great. So we've been using the Z table. Another thing that we could do is we could just approximate areas under the curve. Now, usually I start with this, but then people get so hung up on using this approximation that they forget that we can get these actual kind of more precise probabilities from the table. But we can use just approximations. Yeah, but I usually get you to solve for the standard deviation, right? So if you have any of these, if you have 3 out of 4 components, you could have to solve for any one of these, right? So not just x, but you could solve for mu, you could solve for sigma, right? Yeah, nice. And usually I get you to solve for sigma, or well, I think there's a question where I ask you to solve for mu, right? So it happens, it happens. Okay. Oh yeah, so we can approximate areas under the curve. So if we don't have a Z table, right, then we can use these approximations and we can get a pretty good idea of the areas under the curve. So if we don't have a Z table, all right, or software, so R or Excel or whatever you want to use, okay, we can approximate areas under the curve. So what does that mean? That the areas under the curve are probabilities, right? And so if we're approximating areas under the curve, really what we're doing is approximating probabilities. Okay, so if we don't have a Z table, we can approximate areas under the curve and areas under the curve, oops, our probabilities. Right. Okay, how? We call it the 68, 95, 99.7 rule, which is also called the empirical rule, but usually I just call it kind of by that name. So I guess I didn't finish this sentence. Using the 68, 95, 99.7% rule. Oh boy, what does that mean? This is, I'll just make a note here, maybe in dark green or something. It's also called the empirical rule. But I'm just going to call it the 68, 95, 99.7 rule, only because that really tells us what's going on. So what does it say? It says that if you have moved one standard deviation on either side of the mean, then you have the central 68% of the curve. Okay. If you move out 2 standard deviations, then you've covered the central 95% of the curve. If you've moved out 3 standard deviations, you've covered the central 99.7% of the curve. Okay. And there's a graphic that I'm going to steal because I always try to draw it and then I really blub it. Okay. So here they've made this beautiful, this beautiful graphic. I don't know how they did it. They must have programmed like crazy. Because I've tried, but it's really hard. Okay, I guess it can go here. Okay, so what the 68, 95, 99.7 rule says is that if I move out from the mean, right, and I move out 1 standard deviation on either side, then I have the central 68%, right? So the central part is really important. Then if I move out 2 standard deviations, right, I've covered the central 95% of the curve. Okay. If I know that I have the central 68%, for example, then how much area is in the lower tail, right? So if I've moved down 1 standard deviation, what's the probability of being less than that, right? Just using the approximation. Well, if I've got the central 68% here, and I remember that my curve is symmetric, then 1 minus 0.68 must be the leftover, right? But then I have to split that evenly amongst the tails, right? So for example, right, we can use the approximations to find approximate probabilities in the tails, to find approximate probabilities in the tails. Right, so for example, an observation is 1 standard deviation below the mean, right? What's the probability of seeing something less than that? Okay. Or maybe I'll rephrase it. What is the probability of observing something more than 1 standard deviation below the mean? More, or that's kind of confusing. More is higher. Something more extreme than 1 standard deviation below the mean. Okay. So then I'm relying on this approximation. So, okay, I moved down 1 standard deviation below the mean. So now I can say, okay, well, at 1 standard deviation, that's a cutoff, right? But it's for the central 1 standard deviation. So here, if I draw this out, oops. Here I've got mu, and then I've got mu minus 1 standard deviation, right? So then here, right, this is the cutoff, right? This generic cutoff that I'm talking about. And we want to know what's the probability of seeing something more extreme meaning into the tails. I'm going to start introducing that terminology because we're going to rely on it a lot later, right? What's the probability of seeing something more extreme than what we saw, right? So if you're in the lower end, more extreme would be the lower tail. If you're on the upper end, more extreme would be in the upper tail. Right, so here, more extreme, right, is really just into the tail. So potentially. Okay. So what we want to find is we want to find or approximate this area, right? Not using a table anymore, because mu minus sigma, if I move down 1 standard deviation, right, then this would be a z-score of 1, right? So we're going to check our work, right, using the z table. But first, let's use this approximation. Okay, so the approximation says that, okay, here at mu plus sigma, right, in here, I've got an area of 0.68. Which means that I have 1 minus 0.68 left over, which is 0.32, but I have to split it evenly amongst the tails. So from here and here, I have 0.32 divided by 2, which is 0.16. But let me just confirm. 0.16 and 0.16. Right. So now, right, the area that I'm interested in, I just found, is approximately 0.16. The probability is approximately 0.16. Good. So now let's confirm this with the z-score. We can confirm this with the z table. Okay. So if my observation is mu minus sigma, right, that's kind of weird. So then x is going to be, if we let x be mu minus sigma, math, right? You guys like math. I'm used to my stat 121s. They're from like the arts and they don't like math. You guys like it. So, or at least I'm telling you do. Z is x minus mu over sigma, right? Z, if x is going to be mu minus sigma, I'm going to write that in brackets, mu minus sigma minus mu over sigma. My OneDrive is driving me nuts. Mu minus sigma minus mu, of course, right? Now I have negative sigma over sigma. Why is that important? Why is it important that we retain the negative? Well, because I'm below the mean, right? So it is important, right? And so now Z is negative sigma over sigma. So Z must be negative 1.00. So now using the Z table, right, I can go and I can find Z, which is negative 1 even, right? So using the Z table, we find what? So it's negative. So again, I'm going to steal this top portion, but it's way down here, negative 1.0. Sorry, it's catching up. So I'm going to do this in two parts. And oops. There. So again, right, this just keeps going, keeps going. So if I have a Z of negative 1 even, right, then I go negative 1.00, right? So we don't have to highlight very much. I'll do this whole row, but then this is the one that we want. So then the area to the left of Z equal to negative 1.00 is more precisely 0.1587, right? But if you think about it, that's pretty close to 0.16, right? And so that's why this 0.16 is an approximation, right? And so it's not quite as precise as we could get, but if you're just looking for a rule of thumb, right, then the 68, 95, 99.7 rule is going to serve you well, right? It's going to give you a good idea of what those probabilities are. So therefore, the probability, and maybe I'll use the probability notation, the probability that Z is less than or equal to negative 1.00 is 0.1587, right? Notice that this is more precise than our approximation of 0.16. But 0.16 is really close, right? And so, but it's still a good approximation. Okay? But 0.16 is still a good approximation. Yeah. Good. Nice. So then in business, there are things called Six Sigma, right? Which is like an efficacy model. And I think what it's referring to, I've never really confirmed. Let me go back here, right? But Six Sigma is how many standard deviations we can fit under the curve until we're at 99.7% of the curve is between the 6 standard deviations, is in a length of 6 standard deviations. So really these tails, right, what's left in the tails is 0.3%. While split evenly amongst the tails, there's very, very little probability of exceeding 3 standard deviations, right? So even at 2 standard deviations, there's only 5% left over. And so split evenly amongst the tails, it's only 2.5%, right? So even being further than 2 standard deviations away from the mean is going to be considered extreme. Okay. And we'll talk more about that as we get further into the material, but I think that's a good place to stop today. If you have any questions, let me know. Otherwise, thanks for coming, and I hope you have a great long weekend. Stop this recording here.